Welcome to this exciting problem walkthrough. Today, we'll be exploring problem number 518, titled Coin Change 2. This problem is a classic dynamic programming challenge that focuses on finding the number of ways to make up a given amount using a set of coins. It's a fantastic exercise for improving your problem-solving and algorithmic skills. Let's dive in together. In this problem, you're tasked with finding the number of ways to make up a given amount of money using coins of specific denominations. The coins array represents the values of the coins available, and the amount is the total sum you need to form. If it's not possible to make up the amount using any combination of the coins, you should return 0. Additionally, you can assume that you have an unlimited supply of each type of coin available. For example, if the coins array is 1, 2, 5, you can use as many 1s, 2s, or 5s as needed to form the combinations. The input format specifies that the coins array can have between 1 and 300 elements, each between 1 and 5,000 in value, and the amount can range from 0 to 5,000. Your task is to return an integer representing the total number of possible combinations to achieve this amount using the given coins. Let's look at a few examples to clarify the problem. In the first example, the coins array is 1, 2, 5, and the target amount is 5. There are 4 distinct ways to make up this amount: using a single coin of 5, using 2 coins of 2 and 1 coin of 1, using 1 coin of 2 and 3 coins of 1, or using 5 coins of 1. Therefore, the output is 4. In the second example, the coins array contains only one denomination, 2, and the target amount is 3. Since 3 cannot be formed using a coin of denomination 2, the output is 0. Finally, in the third example, the coins array is 10, and the target amount is 10. Here, there's only one way to form the amount, by using a single coin of 10, so the output is 1. These examples illustrate how the combinations depend on both the values in the coins array and the target amount. Now, let's review the constraints and additional notes for this problem. The number of coins in the array can be as large as 300, and each coin's value can go up to 5,000. All the coin values are guaranteed to be unique, and the target amount can range from 0 to 5,000. Importantly, if the amount is 0, there's always exactly one solution, using no coins at all. Another key point is that the order of coins in a combination doesn't matter. For instance, 2, 1 is considered the same as 1, 2. Since both the coins array and the amount can be quite large, the solution needs to be efficient. Leveraging dynamic programming is essential to handle these larger inputs and compute the number of combinations effectively. When tackling the coin change 2 problem, the brute force approach might be the first to come to mind. The idea behind this method is straightforward: generate all possible combinations of coins and check whether their sum matches the target amount. This is often implemented using recursion and backtracking. For each coin, you have 2 options: either include it in the current combination or skip it. This choice structure forms a decision tree, but the major downside is that the number of combinations grows exponentially as the size of the coins array and the target amount increase. This leads to a time complexity of O(2 to the power of n, where n is the number of coins, and a space complexity of O(n) due to the recursion stack. While this approach helps us understand the problem structure, it's not practical for larger inputs because of its inefficiency. A more systematic approach is to use dynamic programming. Specifically, we can use a 2D DP table to track the number of ways to form each target amount using a subset of coins. Let's see how this works in detail. The 2D dynamic programming approach defines a table where dp I, j represents the number of ways to form the amount j using the first I coins. The recurrence relation for this approach is dp I, j equals dp I1, j plus dp I, j coins I1. Here, dp I1, j accounts for the case where we exclude the current coin, while dp I, j coins I1 adds the number of ways to form the amount by including the current coin. This method is effective because it avoids counting duplicate combinations and systematically fills in the table, ensuring no redundant calculations. The time complexity of this approach is O(n) amount, where n is the number of coins, while the space complexity is O(n) amount, due to the storage required for the DP table. However, this space usage can be further optimized. By recognizing that we only care about the current and previous states for a given amount, we can reduce our storage needs significantly. This leads us to the optimized 1D dynamic programming approach. The optimized 1D dynamic programming approach builds on the principles of the 2D method but reduces space complexity by storing results in a single array, dp(j). Here, dp(j) represents the number of ways to form the amount j. To update this array, we iterate over each coin, and for every amount greater than or equal to the coin's value, we apply the recurrence relation, dp(j) plus equals dp(j) coin. This means that for each amount, we add the number of ways to form the remainder after including the current coin. By iterating over coins first and then amounts, we ensure that combinations are counted correctly. This approach captures the cumulative state efficiently, so instead of maintaining a 2D table, we only track the relevant results in a 1D array. The time complexity remains O, an asterisk amount, but the space complexity is now reduced to O, amount, making this method both time efficient and space efficient. These optimizations make the 1D DP approach particularly suitable for solving larger instances of the problem. Given the trade-offs between these approaches, the 1D DP method emerges as the most practical solution. It strikes the best balance between time efficiency and space optimization. Transitioning from the 2D DP table to a 1D array is not only intuitive but also eliminates redundant storage without sacrificing clarity or correctness. While the brute force approach highlights the problem's combinatorial nature, its exponential growth makes it infeasible for larger inputs. The 2D DP method, on the other hand, provides a solid computational foundation but requires more memory than necessary. The 1D DP approach leverages the insight that only the current and previous states are needed to calculate the result, leading to a scalable and efficient solution. This progression from brute force to 2D DP, and finally to the optimized 1D DP, represents the aha moment, a recognition that space can be conserved without compromising on the problem's requirements. This makes the 1D DP approach the clear choice for solving coin change 2 in real-world scenarios. To solve the coin change 2 problem, we need to determine the minimum number of coins required to form a given target amount using a set of coin denominations. If it's not possible to form the target amount, we return -1. The approach we use here is dynamic programming, specifically the bottom-up method. The idea is to break the problem into smaller subproblems and build the solution iteratively. We define a DP array where each index I represents the minimum number of coins needed to form the amount I. First, we initialize the DP array with a size of target +1. Every value is set to infinity, except for DP, 0, which is set to 0 because no coins are needed to form the amount 0. This ensures we have a solid base case. From there, we define the transition relation, which helps us compute the minimum coins for each amount iteratively. The transition relation is the key to updating our DP array. For each amount I, we calculate DP, I, as the minimum of its current value or DP, I coin, +1. Here's how it works. DP, I coin, gives us the minimum number of coins needed for the remaining amount after subtracting the current coin, and we add 1 to account for the coin itself. This ensures that we're considering the optimal solution for each amount. Next, we iterate over all the coins provided in the input. For each coin, we update the DP array for all amounts from the coin's value up to the target. By the end of this iterative computation, DP, target, will contain the minimum number of coins needed to form the target amount. Finally, we check the result. If DP, target, is still infinity, it means the target cannot be formed with the available coins, so we return -1. Otherwise, we return DP, target, as the solution. Dynamic programming is particularly well suited for this problem because it leverages overlapping subproblems and optimal substructure. Overlapping subproblems occur because we repeatedly compute solutions for smaller amounts as part of solving for larger amounts. Optimal substructure means that the solution to the overall problem depends on optimal solutions to its subproblems. For initialization, setting DP 0 equals 0 ensures we have a solid starting point, while initializing other values to infinity allows us to handle amounts that cannot be formed. The order of processing is crucial. For each coin, we process amounts starting from its value up to the target. This ensures we account for each coin correctly and use it as many times as needed. Additionally, this approach is space efficient because we only maintain a 1D DP array of size target +1, avoiding the overhead of recursive calls with memoization. The primary data structure in this approach is the 1D DP array. Each index in this array represents an amount, and the value at that index represents the minimum number of coins required to form that amount. Another essential data structure is the list of coins, which allows us to iterate over all available denominations and update the DP array accordingly. When analyzing complexity, the time complexity is O, target asterisk n, where n is the number of coins. This is because, for each coin, we process all amounts up to the target. The space complexity is O, target, since we only use the DP array, making this approach efficient in terms of memory usage. Together, these properties make the dynamic programming solution both time and space efficient for this problem. To better understand the algorithm, let's walk through an example with coins 1, 2, 5, and a target of 11. We start by initializing the DP array as 0, INF, 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 INF. This represents the minimum coins needed for each amount from 0 to 11. First, we process the coin 1. For each amount from 1 to 11, we update the DP array by considering combinations that include coin 1. Next, we process coin 2, further minimizing the DP values for amounts that can be formed using this coin. Finally, we process coin 5, which reduces the DP values for higher amounts like 5, 10, and 11. After all coins have been processed, the final DP array is 0, 1, 1, 2, 2, 1, 2, 2, 3, 3, 2, 3. The value at DP, 11, is 3, which means the minimum number of coins needed to form the target 11 is 3. This solution implements the classic dynamic programming approach to solve the coin change 2 problem. The problem asks us to determine the number of ways to make a given amount using a set of coin denominations. We begin by initializing an array DP of size amount plus 1 to represent the number of ways to make each amount from 0 to the target. Initially, all values are set to 0, except for DP, 0, which is set to 1. This represents the base case. There is exactly one way to make the amount 0, which is by using no coins. Next, we iterate through each coin in the coins array. For each coin, we update the DP array for all amounts greater than or equal to the coin's value. Specifically, if we can already make the amount x a coin, then we can make the amount x by adding this coin. Thus, we add DP, x, coin, to DP, x. By the end of the process, DP, amount, contains the total number of ways to make the target amount using the given coins. The algorithm is efficient, operating in O, amount asterisk n, where n is the number of coins, and O, amount, space due to the DP array. This makes it well suited for the problem's constraints. This is the Java implementation of LeetCode problem number 518, coin change 2. It mirrors the logic of the given Python solution. The code uses an integer array DP to store the number of ways to make each amount from 0 to amount. The outer loop iterates through each coin, and the inner loop updates the DP array for all amounts greater than or equal to the coin's value. Key differences from Python include the use of type declarations and Java's syntax for array initialization. The solution ensures optimal space and time complexity using dynamic programming. The problem coin change 2 challenges us to determine the number of possible combinations of coins that sum up to a given amount. The key here is that each coin can be used an unlimited number of times. To solve this efficiently, we use dynamic programming with a one-dimensional DP array. In this array, DP, x, represents the number of ways to make the amount x using the given coins. For example, if the amount is 5 and the coins available are 1, 2, 5, we start by initializing the DP array. Initially, DP is 0, 0, 0, 0, 0, 0, where the size is amount plus 1. We set DP 0 equals 1 because there is only one way to make the amount 0, which is by using no coins. This setup forms the foundation for our solution. Now we begin iterating through the coins one by one. Starting with the first coin, which is 1, we update the DP array for all amounts from 1 to 5. For each amount x, we add the value of DP, x, coin, to DP, x, representing the number of ways to form x by including the current coin. For the coin 1, the updates are as follows. At x equals 1, DP 1 becomes 1, at x equals 2, DP 2 becomes 1, and this continues until x equals 5, where all values in the DP array are updated to 1. Now, moving to the coin 2, the range starts from 2 to 5. Using the same logic, we update dp2, adding dp2 to 2, which results in dp2 becoming 2. Similarly, dp3, dp4, and dp5 are updated, reflecting the combinations that include the coin 2. At this stage, the dp array accounts for combinations using both coins 1 and 2. Next, we consider the coin with a value of 5. Here, we only need to update the dp array for the amount 5. We add dp5 to 5 to dp5, which increases dp5 to 4. This final dp state indicates that there are 4 different ways to make the amount 5 using the coins 1, 2, 5. To illustrate another example, consider amount equals 3 and coins equals 2. After initializing the dp array as 1, 0, 0, 0, we process the only available coin, 2. For x equals 2, we update dp2 by adding dp2 to 2, resulting in dp2 equals 1. However, dp3 remains 0 since no combinations exist to form the amount 3 with the given coins. This demonstrates how the dp array dynamically reflects valid coin combinations for each amount. To further illustrate, let's examine the case where amount equals 10 and coins equals 10. The dp array is initialized as 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. The only coin available is 10, so we update the dp array for x equals 10. Adding dp 10 to dp 10 results in dp 10 equals 1. This tells us that there is exactly one way to make the amount 10 using the coin 10. This example emphasizes how the dp array is updated only for amounts that can be formed with the available coins. It also demonstrates that when no valid combinations exist, the dp value for that amount remains 0. The key takeaway from this solution is that the dp array dp efficiently tracks the cumulative number of ways to form each amount. By iterating over the coins in sequence, we ensure that each combination is counted only once, avoiding duplicates. For example, a combination using 2 5-value coins is distinct from a combination using a single 10-value coin. Regarding complexity, the time complexity is O, amount * len, coins, as we iterate over each coin and update the dp array for all relevant amounts. The space complexity is O, amount, as the dp array size depends only on the target amount. This approach balances efficiency and simplicity, making it a robust solution for the problem. The time complexity of this solution can be understood by analyzing the 2 main loops in the algorithm. First, the outer loop iterates over each coin in the given list of coins. If the number of coins is represented as n, this loop will run n times, once for each coin. Then, for each coin, the inner loop iterates over all relevant amounts starting from the coin's value up to the target amount. If the target amount is m, the inner loop can run at most m times for each coin. Now, when we consider the total number of iterations across all coins, in the worst case, where all coins are small, for example, all coins have a value of 1, the inner loop effectively runs m times for each of the n coins. This leads us to the final time complexity of the solution, which is O, n * m, where n is the number of coins and m is the target amount. When analyzing space complexity, the key factor to consider is the memory used by the algorithm. The primary contributor is the dynamic programming array, or dp array, which is used to store the number of ways to form amounts from 0 to the target amount m. The size of this array is m plus 1, meaning its space usage is O, m. Additionally, the algorithm only uses a constant amount of extra space for variables like the current coin being processed in temporary calculations. This constant space usage is O, 1. When we combine these factors, the overall space complexity of the solution is dominated by the dp array, resulting in a total space complexity of O, m. To evaluate the best, average, and worst-case scenarios, we find that the time complexity remains consistent across all cases. In the best case, the algorithm must still process all coins and amounts, leading to a time complexity of O, n * m. Similarly, the average case is also O, n * m, as every coin and amount is processed due to the nested loop structure. In the worst case, where all coins are small, such as having a value of 1, the inner loop executes the maximum number of times, resulting in the same time complexity of O, n * m. Comparing this to a brute force approach, the difference becomes apparent. A naive solution would involve recursively trying every possible combination of coins to reach the target amount, resulting in an exponential time complexity of O2 to the power of n, where n is the number of coins. This brute force method also requires significant stack space for recursion, leading to high space complexity. Clearly, the dynamic programming approach is far more efficient. The dynamic programming approach offers several key advantages. By leveraging overlapping subproblems, it avoids redundant calculations, thereby reducing the time complexity to O(n*m). This is a significant improvement over the brute force approach, which has exponential complexity. Additionally, the space usage is minimized to O(m) by maintaining a single DP array, making it much more memory efficient. To mathematically verify the time complexity, consider that for each coin, the algorithm iterates through amounts ranging from the coin's value up to m. This means the inner loop contributes at most m iterations for each coin. With n coins and m iterations per coin, the total number of iterations becomes proportional to n*m. Thus, we conclude that the time complexity is O(n*m), while the space complexity is O(m), thanks to the compact DP array. When solving coin change problems, there are several common mistakes to watch out for. First, it's important to ensure that you only count unique combinations of coins. For example, combinations like 1, 2, 1, and 1, 1, 2 represent the same solution, but failing to account for duplicate combinations can inflate your results. To avoid this, make sure to standardize the order of coins or use a dynamic programming approach that inherently avoids duplication. Another frequent pitfall is relying on naive recursion without memoization. This leads to redundant calculations, where smaller subproblems, like solving for a target of 3 while solving for 5, are calculated multiple times. Optimizing with memoization or dynamic programming not only eliminates this inefficiency but also drastically improves performance. Additionally, misunderstanding base cases is another area where mistakes occur. For instance, it's crucial to remember that there's exactly one way to make a sum of 0 by using no coins at all. Forgetting this can lead to incorrect initialization in your recursive or DP solution. Finally, blindly applying greedy algorithms can lead to suboptimal results. While they work for certain coin denominations, they fail for others. A good example is making a target of 6 using coins 1, 3, 4. A greedy approach might incorrectly choose 4, 1, 1 instead of the optimal solution, which is 3, 3. Being mindful of these common mistakes will help you avoid errors and implement a more robust solution. Edge cases are another critical area to address. For instance, what happens if the coin array is empty or the target is 0? These scenarios can cause runtime errors or incorrect results if not explicitly handled. Testing edge cases ensures that your solution is robust and doesn't fail for unexpected inputs. When it comes to interviews, it's crucial to understand the variations of coin change problems. Some variations require counting combinations, while others ask for the minimum number of coins. Before you start coding, be sure to clarify the exact requirements with your interviewer to avoid solving a different problem. Additionally, be prepared to discuss the trade-offs between approaches. While brute force methods are simple and easy to understand, they come with a high computational cost of O2 to the power of n. On the other hand, dynamic programming is far more efficient, with a time complexity of O, target *n, but it requires careful initialization and additional space. During the interview, focus on explaining your thought process clearly. For example, you could say, I'm choosing a bottom-up DP approach to avoid stack overflow issues that might arise with recursion. Finally, remember to optimize for large inputs. Interviewers often test scalability by using large test cases. A solution that works on small inputs but fails on large ones will not be sufficient. Ensuring that your approach handles these scenarios efficiently demonstrates your ability to write scalable code. Coin change problems are closely related to several other problem types, and it's helpful to understand these connections. For example, in LeetCode 322, the goal is to find the minimum number of coins required to make a target amount. In contrast, LeetCode 518 focuses on counting the number of unique combinations to achieve the target. Then there's LeetCode 39, Combination Sum, where the task is to find all unique combinations of numbers that sum up to the target. Finally, LeetCode 377, Combination Sum 4, introduces an additional twist by counting combinations where the order of numbers matters. Exploring these related problems can deepen your understanding and help you recognize patterns that apply across different scenarios. When it comes to alternative approaches, dynamic programming is often the most efficient, particularly the bottom-up version, as it avoids recursion stack issues and scales well with larger inputs. Recursive backtracking can be a useful learning tool, especially when combined with memoization to improve efficiency. However, it's typically slower due to the overhead of recursive calls. Greedy algorithms, while intuitive, should only be used when the coin denominations allow it, such as specific cases like US currency. Otherwise, they may fail to find the optimal solution. Lastly, breadth-first search can be an iterative alternative for exploring all possible combinations. It's especially useful in problems requiring the shortest path, such as finding the minimum number of coins. By understanding these approaches and their trade-offs, you'll be well prepared to tackle a variety of coin change problems effectively. Great job making it to the end. In this session, we explored how to solve problem number 518, Coin Change 2, using different approaches like brute force and dynamic programming. We covered key concepts, optimization strategies, and takeaways to help you tackle similar challenges in the future. Thank you for watching, and don't forget to like, subscribe, and share your feedback. Keep practicing and happy coding. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!